Welcome to Lecture 5, in which we look at motion in 2 and 3 dimensions. Now, everybody's thinking about 3 dimensions these days because 3D movies are all the rage. But if you think about it, the world around you is 3D already. I remember a story, actually an anecdote from my childhood. When 3D movies first came out, they were nowhere near as advanced as today's 3D movies. And one of my neighbor kids was telling my mother about how we had just seen a 3D movie. And my mother said, "Well, life is 3D." And the kid said, "Huh?" As if somehow 3D was only in the movies. Well, 3D is all around us. And if we want to describe motion in all its details and in all its richness, we need to deal with 3 dimensions. One reason dealing with the different dimensions is obviously important is because the direction of motion is crucial. If you want to go to Boston, you go one direction. If you want to go to New York, you go a different direction. Where you end up depends on what direction you go. We already saw directionality in the case of motion in 1 dimension, but it was just along a single line, back and forth, positive or negative. In 3 dimensions, we have the richness of directions in every possible way. We can go in any way in space, and that greatly expands the richness of what phenomena can happen, and it also makes the mathematics of describing motion more complicated. So we're going from plus or minus in 1 dimension to some way of describing this whole vast richness of directions we can have in three dimensions. Remember that velocity is the rate of change of position. It describes direction as well as speed, and velocity is going to become a much richer concept now as we move into 3 dimensions, or even 2 dimensions, as we'll often use. So we have to introduce a new mathematical tool. And the new mathematical tool is called the vector. And I'm just going to give you a brief description here of some of the mathematics we use to handle vectors. So I want to begin with the paradigm vector, which is a vector that describes displacement. So what I have here is some origin, which I have called O, and some other point, which I've called P. And I want to describe somehow the relationship in the 2-dimensional space of this screen between those 2 points. And so I would draw this arrow, and that arrow is called a vector, and that arrow indicates by its length how far it is from the origin O to the point P. It represents by its direction what the actual direction is if you go from O to P. That is the displacement vector from O to P, or because O is the origin, the point at which we measure positions from, this is also simply the position vector. P is the position, the point we want to be at, and this arrow describes where that position is relative to the origin. So that geometrical object whose length talks about how far it is from O to P and whose direction talks about the direction from O to P describes in 2 dimensions, and could easily do so also in 3 dimensions, everything there is to know about the relationship in space between O and P. So the vector becomes what was in 1 dimension just a signed number, positive 3 meters, negative 3 meters, whatever. The vector is more complicated to describe. Right now I'm just simply talking about the vector and saying, well, it's a vector from O to P. It's kind of up at this angle. I could give you the exact angle relative to some axis I chose, like the horizontal or the vertical or some arbitrary axis. I could also tell you how far you'd have to walk horizontally and how far you'd have to walk vertically to get to point P. All those would be ways of describing mathematically what that vector is about. Now we can do things with vectors. We can add vectors, we can subtract vectors, we can multiply vectors by numbers. We can actually also multiply vectors by vectors, but that's going to come much later. Today we'll be looking at adding vectors, subtracting vectors, and multiplying vectors by numbers. So here is this vector. I'll call it R. I'm going to use the symbol lowercase r to stand for radius. This is sort of a radius vector from this origin. It's a distance from the origin and a direction from the origin. And I'm going to put over every quantity that's a vector a little arrow. And that's going to be crucial. My students know that they get 1 point off if they leave off that vector arrow. If they write R without a vector sign equals something else with a vector sign, it's wrong. Because a vector is a new kind of mathematical quantity that is deeper, richer than simply a number. Because it has both magnitude, how big it is, and its direction. And so we're going to designate vectors by putting that arrow over them, and that arrow is going to be crucial. So every time you see that arrow, you're talking about a quantity that has both magnitude and direction. And the paradigm such quantity is displacement, which will be designated, displacement will be delta r. Position itself, measured with respect to some origin, will be given by the vector r. So suppose now I have another point Q over here. So I've got the origin, I've got point P, and I've got point Q. And after I get to point P, I want to go to point Q. So I march along, and there's a different vector that describes the displacement from P to Q, and I'll call that a change, delta again, the delta symbol for change. So that's going to be the vector delta R. So delta R is the change in position when you go from P to Q. And now I want to define adding vectors. Because if I go from O to P and then from P to Q, the effect is the same as if I went from O and ended up at Q. So this vector from O to Q, this arrow with this length and the direction that arrow has, describes a trip, direct trip from O to Q. So that's the sum of the vectors R and delta R. That defines the sum. So that's R plus delta R. And I'm going to use the same mathematical operators, addition, subtraction, multiplication, things like that, that I use with regular numbers. But they're going to have richer meanings with vectors. So this is the position vector and the displacement vector, and we'll get soon to other vectors as well. But there's how we add vectors. We simply take one vector, take another vector, put its tail at the head of the first vector, go to where its head is, and then draw from the tail of the first vector to the head of the second vector, and that vector that results is the sum. Now, we could do that mathematically. We could use the law of cosines. We could put it on a graph. We're not going to get into all those details here, but we will use this concept of vector addition and vector subtraction in the next few lectures. What happens when we want to multiply a vector by a number? A number is called a scalar. A scalar is a number that doesn't have direction. All it is a number. Plus 1 is a scalar. Minus 2 is a scalar. It doesn't have a direction. It's not at 45 degrees. It's not represented by an arrow. So a vector is a quantity with magnitude and direction. A scalar is a quantity without direction, just a number. So here's a vector v. Again, it's a vector because it's got that arrow over it. Here's vector 2v. It's a vector in the same direction, but it's twice as long. Here's the vector minus v. It's a vector of the same length as v, but it's in the opposite direction because the minus 1 flipped its direction. So that's what it means to multiply a vector by a scalar. And finally, I want to introduce what it means to subtract vectors, because that will be important to us frequently because we're going to want to look at deltas, at changes. So what's the vector R2 in this case minus R1? Well, by definition, it's the vector I'd have to add to R1 to get R2. So there it is. If I want to get to the endpoint of R2 and I'm at the endpoint of R1, I've got to add this vector, which I'll call delta R. It's the difference of R2 minus R1. So one way of looking at subtracting vectors, the vector difference is the vector I have to add to the second vector to get the first. Another way to look at it, what's R2 minus R1? Well, there was my first definition, but another definition is it's the vector I get by adding the vector R2 and the vector minus R1. Because one way of thinking of R1 minus R2 minus R1 is it's R2 plus minus R1. So let's do that because we know how to multiply a vector by minus 1. It just flips its direction. So there's minus R1 because R1 was a vector that went up like this. So here's minus R1. It doesn't matter where the vector starts. I can move it around. All that matters about the vector is its length, that is its magnitude, and its direction. So I can move the vector all around because where it starts is not relevant. So there's minus R1, and I add those two. I go along R2, I go along R1, and there's the vector delta R equals R2 minus R1. Before it was up here, doesn't matter. Where a vector starts is not important. All that's important is the length of this vector and its direction, in this case horizontally to the right. So that's how we subtract vectors. That's vector arithmetic. So now let's talk about vectors in physics. Vectors in physics are going to be used to represent the quantities we've talked about for describing motion. So let's look at some examples. So here is the velocity vector. The velocity vector is the rate of change of position. The position vector I just introduced is delta R. The velocity vector is v. V is delta R divided by delta t. How do you divide a vector by something? Well, delta t, dividing by delta t is the same as multiplying by 1 over delta t, so we know how to do that also. So the vector velocity is defined as the rate of change of position, just as it was before, but now position is a richer quantity, it's a vector quantity, and you'll notice that I have carefully put the arrows over both the v and the r to indicate that these are vector quantities. So the object's average velocity during a time interval delta t is the change in its position, that is its displacement, delta r, during that time interval, delta t. There's the time interval. So that's the anatomy of the equation that now defines velocity for us in the full richness of multiple dimensions. Well, we can do the same thing for acceleration. Acceleration is the rate of change of velocity, just as velocity is the rate of change of position. So again, with the arrows over these quantities, a with an arrow over it is the vector acceleration. Its magnitude is the acceleration in meters per second squared, whatever that comes out to be, and its direction is the direction in which the velocity is changing, which is not necessarily the same as the direction of the velocity. That's going to become a really important point, and that's something that's really rich about multiple dimensions. In one dimension, we just had the possibility of an acceleration in the same direction as the velocity, speeding something up, in the opposite direction, slowing it down. But in 2 and 3 dimensions, we have a much richer possibility. The orientation of the acceleration can be arbitrary in relation to the velocity. So here's the anatomy of the equation for acceleration. The object's average acceleration during a time interval delta t is found by taking the change in the object's velocity, delta v, the final velocity vector minus the initial velocity vector, and divided by that time interval. So there we now have the generalizations of our definitions of velocity and acceleration to multiple dimensions with the time interval delta t. So 2 and 3D are far richer than the one-dimensional motion for reasons I described. Any change in velocity, and I said this in the last lecture, and I'm going to say it again and again and again, any change in velocity represents an acceleration. That could be a change in the magnitude of the velocity vector, it could be a change in the direction of the velocity vector, or it could be a change in both of them simultaneously. Let's take a look at an example. So I want to emphasize that the word acceleration does not just apply to speeding up. You have to broaden your sense of what acceleration means. It's not just speeding up. Here it is speeding up. The car is going faster and faster and faster. Okay, let's look at what went on there. It had some initial velocity when it started out. It had some final velocity. The final velocity in this case was in the same direction. The final velocity vector arrow is longer because it represents a larger speed, the magnitude of the velocity, but it's in the same direction because in this case the car's direction never changed. It did undergo acceleration, and if I take those two vectors and subtract them by taking v initial, taking minus v initial, which is the other way, adding it to v final, I get a small delta v vector that represents the difference in length of these two. It's the difference in length in this case because these two vectors are in the same direction. It's not always that simple if the directions are different. There's delta v, and whatever time interval was involved in this car's trip from the left side of the screen to where it ended up, divide by that time, divide delta v by that time, and I have acceleration. I can't compare the sizes of the velocity and acceleration vectors because that's like comparing apples and oranges. They're measuring different quantities. So that is acceleration as you knew it before and as it describes one-dimensional motion. But I want to emphasize, it's not just speeding up. So here's a car that's going around a corner. At a constant speed, if you were driving that car and looking at the speedometer would read 25 miles an hour the whole time. You say, well, my speed isn't changing, I'm not accelerating. But you are accelerating. And the reason you're accelerating is because there's your initial velocity, it was to the right. There's your final velocity, it's the same length, the same magnitude, the same speed, but it's in a different direction. So, did the velocity change? Yes, the velocity changed. Did the speed change? No, the speed didn't change, but the velocity changed. And let's do the vector arithmetic of that. Here was the initial velocity, here was the final velocity. The difference between them, delta v, is the vector I'd have to add to the initial velocity to get the final velocity. There's delta v. Delta v is at an angle. It's not in either the initial or final direction, and if I divide that delta v by the time interval over which that velocity change took place, I've got an acceleration, and the acceleration is in the same direction as the change in velocity. Notice it is not in the same direction as either the initial velocity or the final velocity. The direction of change in velocity does not have to be the same as that of velocity, and that means acceleration and velocity do not have to have the same directions. And let's summarize these findings about velocity and acceleration and their relationships. First of all, they do not need to be in the same direction. Second, the acceleration in the same direction as the velocity, as we saw in that first example with the car only serves to increase the speed. That's your old-fashioned gut feel for what acceleration means. Acceleration opposite the velocity, and we saw an example of this in a one-dimensional case in the previous lecture, decreases the speed, but doesn't change the direction. And if the acceleration is at right angles to the velocity, and I'm going to prove this rigorously in the next lecture, then the only thing that changes is the direction. But that's still an acceleration. You can be accelerating with your speed staying constant as long as your direction is changing. And one of the biggest misconceptions I see in students of introductory physics is forgetting that changing direction is just as legitimate an acceleration as is changing speed. And both could happen simultaneously. So let's now do what we did in the last lecture. We started out in general talking about motion in one dimension last time, and then we looked at the special case of motion under the influence of gravity near Earth's surface. Let's do the same thing here. So let's talk about the motion under the influence of gravity, but now it can be two-dimensional motion. And again, I emphasize, we're going to set up a coordinate system. That coordinate system is a pure human artifact. Our coordinate system, as I suggested last time, is going to have the x-axis horizontal, the y-axis vertical, and that's useful for a very powerful reason. It turns out that the motion of an object in the horizontal direction is completely independent of the motion in the vertical direction. And because the motion in the vertical direction under the influence of gravity is motion with constant acceleration, we can understand the vertical motion exactly as we did last time in lecture number 4. We can understand horizontal motion even easier because in the absence of any other forces than gravity, the motion is unaccelerated and the object moves at constant velocity. And I'd like to do a demonstration now that shows you just how that works. So what I have here is just a little bracket with a screw on it, and the screw is magnetized, and I'm going to hang a steel ball from that screw. And I have another identical steel ball, identical in size and mass, and I'm going to roll that ball along, and it's going to hit the ball that's hanging there, and they're both going to go off in the kinds of paths that objects describe when they're under the influence of gravity alone in two dimensions. However, for reasons I'm going to prove rigorously and mathematically in lecture 14, when an object hits another one of the same mass, and the first object is moving and the second one's at rest, the first object stops completely and the second one takes off with the initial velocity of the first one. So this ball is hanging just over the edge of the table. What's going to happen is the ball that hits it is going to stop and it's going to fall vertically. Its motion is going to be purely vertical. The second ball, the one that's now hanging from that little magnetic screw, is going to take off with a horizontal velocity in this direction. But what I want you to watch is what happens as the two balls fall together. The vertical motions are both the same. They're both accelerated motion under the influence of gravity alone. The horizontal motion of the one ball that was struck, the one that's moving horizontally, is completely independent of its vertical motion. So horizontal and vertical motions are independent, and that allows us to analyze motion under the influence of gravity without regard to any new physics. We simply have to say, okay, we understand one-dimensional motion in the vertical direction, constant acceleration. We understand one-dimensional motion in the horizontal direction, even easier, just constant velocity. And we put the two together and we get motion in two dimensions. And so let's look at some of the equations we would use to describe the motion in two dimensions now. So here are our equations. The first equation is the equation we developed for position x in horizontal motion, but it has no acceleration term because gravity is only vertical. So it's x is the initial x position plus any initial x velocity, and I'm now putting a little subscript x on that velocity times the time. The y is full accelerated motion with the constant acceleration of gravity. Y is the initial y position, the initial y velocity, if it happens to have a vertical motion as it starts, and then there's this term minus a half gt squared that comes from the acceleration of gravity. So that's what the equations are that are going to describe motion under the influence of gravity. We have two equations now because we've got two dimensions to deal with. The horizontal dimension in which there's no acceleration, and in the vertical direction in which we have the acceleration of gravity. Horizontal position, initial horizontal position, horizontal velocity, which is constant, and time. Vertical position, initial vertical position, initial vertical velocity, the The vertical velocity is going to change with time, so I have to call it y sub 0, and then the gravitational acceleration, introducing this term, minus a half gt squared, and in all these equations appears time. It's in two places in the vertical equation, because once for the initial vertical velocity and once for the acceleration. I could go through a lot of mathematics, but I'm not going to bother you with that. But I am going to point out what happens if we want to understand the equation that describes the motion of an object moving in general under the influence of gravity. For example, here's my tennis ball. I can take this tennis ball and I can give it an initial velocity, some in the horizontal direction, some perhaps in the vertical direction, and I'm going to release it from my hand, and it's going to go something like that, and it's going to describe that arcing path. We want to understand that arcing path. Again, in this course, we're getting mathematical, so let's do it mathematically. So just to make life simple, I'm going to say wherever I started that object, that's the origin. That's x naught equals 0, y naught equals 0. It's got some initial speed, v naught, but that initial speed was given at some angle. So there's some initial velocity vector, and I'm going to use the Greek symbol theta, as I'm doing consistently throughout this course, for angle. So here's what I'm going to do. I'm going to take the horizontal equation, which was pretty simple. It said x was x naught plus the initial x velocity times time. I'm going to solve that for t. And I'm going to plug it into the y equation where I had t. And t appeared two places in the y equation. Once it appeared just by itself, and once it appeared squared. Linear and quadratic terms. And so I end up with this equation. And if you'd like to challenge yourself a little bit, you could do the mathematical exercise of taking the x equation, solving it for t, taking that and plugging it in for t in the y equation, and you will get this equation I show here if you do a little bit of trigonometry and worry about how the initial x velocity is related to the initial speed and the angle, and how the initial y velocity is related to the initial speed and angle, and the tangent comes in there because, well, I get the ratio of those two. So there's an equation. Now, if you look at that equation describes the vertical position of an object starting at position x equals 0 and y equals 0 with some initial speed v0 at some angle theta to the horizontal. That's going to give us the vertical position as a function now of horizontal position. Time's gone because we solved for it. We're losing some information about what's going on, but what we're gaining is a single equation that describes the trajectory. The ratio of the horizontal velocity, which never changes, to the initial vertical velocity turns out to be the tangent of that angle. The horizontal position, which appears twice, is x. And the result of this, if you remember your high school mathematics, is when you have a quadratic function, you're describing a parabola. And in this case, the function is the vertical position as a function of the horizontal position. And so we've proved that in this case of an object undergoing motion under the constant acceleration of gravity, a good approximation, remember, near Earth's surface, then the result will be a parabolic trajectory. Now, I could go on at great length about this equation and some other things it implies, but I just want to give you a few examples. You might ask the question, at what angle should I throw this tennis ball, for example, in order that it go the farthest? Well, if I throw it straight up, it's going to come right back to my hand, and it's not going to go anywhere. If I throw it above a horizontal surface, but right at the surface, it's going to hit the surface immediately, and it's hardly going to go anywhere. So there must be some angle between those two where it's going to get the maximum range. And not surprisingly, and I could prove this if I wanted to spend 10 minutes doing the mathematics, that angle is 45 degrees. So if I launch this ball at 45 degrees for a given launch speed, which is what my muscles are capable of, I will get the maximum range if I launch that thing at 45 degrees. So let's look at that. Here's a picture that shows you different trajectories, different parabolic trajectories for objects that are launched with the same speed, but with different angles. And what you see are the upper two blue trajectories. It's launched at angles steeper than 45 degrees. And in one case, it doesn't go very far at all. In the next blue case, it goes a bit further. Then you see the red curve that describes what's happening to the parabolic trajectory for the object going at 45 degrees. And you see only one red curve. But you see a blue curve and a corresponding green curve that ends up in the same place. Those are at different angles. In fact, the blue curve is at 60 degrees. That's 45 plus 15. And the upper green curve is at 45 minus 15, or 30 degrees launch angle. And you see, interestingly, that those two have the same range. you might ask yourself which of those gets to the end point sooner. The time was missing from that parabolic equation, but if you went back and solved for the time, you would find, not surprisingly, that the shorter path, the green path, the lower trajectory, gets there a lot faster. But they both get to the same point. They both have the same range. And then the extreme cases are 75 degrees, 45 plus 30, and 45 minus 30 is 15 degrees for the lowest green curve, and you'll notice that those two also end up in the same place. So the maximum horizontal range occurs at a 45-degree launch angle. By the way, again, that's true only in the approximation that we neglect air resistance. If we take air resistance into account, then that result is no longer exactly correct. Launch angles, as I just pointed out, on either side of 45 degrees give equal range. And finally, interesting point to make, if you ask the question, where do projectiles spend most of their time? It turns out, as this movie suggests, that projectiles spend about 71% of their time in the upper half of their trajectory. That's why, by the way, if you see a basketball player leaping into the air, or a ballet dancer leaping, or an ice skater leaping, they seem to float near the high point of their trajectory. They aren't really floating. They're undergoing an up-down, and if they're moving horizontally, a parabolic trajectory. But what's happening is 71% of the time is spent in the upper half of the trajectory. And if you'd like to challenge yourself with a little bit of mathematics, you could pretty easily work that out. That 71%, by the way, is 100 times 1 over the square root of 2, to be exact. So it's actually 70.7 blah, blah, blah percent. If you want to work that out, that will be the answer you get. Well, let's end by looking at some examples of projectile motion, which is quite ubiquitous in our everyday world. So here is a beautiful photograph of an erupting volcano. It's a time-elapsed photograph, and so you're seeing the trajectories of these red-hot objects coming out of the volcano. And you'll notice many, many, many parabolas as described by that motion equation that we developed by solving for the time in the horizontal equation and plugging it into the vertical equation and getting an expression for the vertical position as a function of the horizontal position. So that's a beautiful aesthetic example, but there are many other examples of projectiles. The trajectory of a basketball on its way to the basket is a parabolic trajectory described by that equation. We have a fireworks rocket exploding. The fireworks rocket itself was on a parabolic trajectory before it exploded, and when it exploded, all the individual pieces are on their own parabolic trajectories determined by the individual starting velocities and starting positions. They all had the same starting position, but they had different starting velocities, different speeds and directions. They went different ways. The fountain is another beautiful example. You can see the water illuminated by those lights below, undergoing parabolic trajectories. And finally, a movie of dolphins undergoing this leaping trajectory as they come out of the water, and those dolphins are all describing parabolic trajectories. Parabolas and projectile motion are universal in the real world. And so let's end by recapping what we've done here. We've looked at motion now in 2 and, by extension, 3 dimensions. We found that motion is described by these richer quantities called vectors that have both direction and magnitude. We discovered that motion in the horizontal and vertical directions under the influence of gravity those two motions are independent, and that allowed us to solve those problems by basically solving 2 problems, one for the horizontal motion with constant velocity, one for the vertical motion with the constant acceleration that we developed back in the previous lecture, and the end result is these beautiful parabolic trajectories of objects moving under the influence of gravity near Earth's surface.